There is a planet where daytime temperatures can melt metal, and yet water ice has survived there for billions of years. This planet is smaller than Earth's moon, but it's so dense it shouldn't exist in its current form. It sits closest to the Sun, yet reaching it is harder than traveling to Pluto. For centuries, Mercury was assumed to be simple, hot, dead, and predictable. But every time we managed to look closer, it contradicted what physics said should be possible. This is the story of Mercury, the extreme planet that breaks the rules. The surface of Mercury presents an environment more hostile than anywhere else in the solar system. The Sun dominates the sky, appearing 2.5 times larger than it does from Earth. Its light arrives with crushing intensity, more than 7 times the solar radiation that reaches our planet. The temperature on the day side reaches 430 degrees Celsius. That's hot enough to melt lead, zinc, and tin. Hot enough that any exposed organic material would instantly burst into flames and turn to ash. The ground itself glows with heat. Rocks radiate infrared energy back into space. The landscape stretches in shades of grey and brown, ancient, cratered, completely airless. No wind disturbs the dust. No weather patterns exist. The sky above the daytime surface is pure black because there's no atmosphere to scatter sunlight. Stars are visible even at noon, scattered across the darkness like diamonds on velvet. The visual effect is disorienting. Brilliant sunlight flooding the landscape below, while cosmic darkness stretches above. The cratered surface tells a story of bombardment. Mercury's face is scarred with impact craters ranging from tiny pits a few meters across to massive basins hundreds of kilometers in diameter. The largest, Caloris Basin, spans about 1,500 kilometers, roughly the distance from New York to Denver. The impact that created Caloris was so violent it sent shockwaves through the entire planet, creating strange terrain on the exact opposite side of Mercury. Where the shockwaves converged, between the craters, vast, smooth plains stretch across Mercury's surface, ancient lava flows that flooded low-lying areas billions of years ago. These plains are darker than the surrounding cratered terrain, evidence of volcanic activity that occurred early in Mercury's history. The planet had a molten interior once, hot enough to drive magma to the surface. That era has long since ended, but its traces remain frozen in the landscape. Walk from sunlight into shadow, and everything changes instantly. The temperature drops catastrophically, not gradually over hours, but immediately. The thermometer plunges to minus 173 degrees Celsius, 600 degrees of difference in a single step. This represents the most extreme temperature swing in the solar system. For comparison, the difference between Earth's hottest recorded temperature in Death Valley, 56 degrees Celsius, and coldest in Antarctica, minus 89 degrees Celsius, is only about 145 degrees. Mercury experiences more than 4 times that range during every rotation. The cause is Mercury's lack of atmosphere. Earth's thick blanket of air moderates temperature, redistributes heat, and creates a buffer between the extreme of direct sunlight and the void of space. Our atmosphere traps warmth, creating the greenhouse effect that keeps nighttime temperatures from plummeting. It circulates heat from the equator toward the poles, from day side to night side, smoothing out temperature extremes. Mercury has essentially no atmosphere, just a thin exosphere where individual atoms are so sparse they almost never collide with each other. The exosphere has a surface pressure of about 10 to the power of minus 15 bars. That's a quadrillionth of Earth's atmospheric pressure. For practical purposes, it's a vacuum. This exosphere can't hold heat or redistribute it. It can't create weather patterns or wind. It does nothing to moderate the temperature. When the sun rises on Mercury, the surface heats rapidly and directly. Solar radiation slams into bare rock with no atmospheric filtering. Nothing moderates that heating. The rock absorbs energy, and temperature climbs steadily throughout the long day. When the sun sets, all that accumulated heat radiates immediately back into space. Nothing traps it. No greenhouse gases exist to hold warmth. The heat escapes as quickly as infrared radiation can travel, and the temperature collapses. The day-night cycle makes this even more extreme. One Mercury day, one full rotation relative to the Sun, lasts 176 Earth days. This happens because Mercury is tidally locked in a 3-to-2 resonance with the Sunday. It rotates 3 times for every 2 orbits. One rotation takes 58 Earth days. One orbit takes 88 Earth days. The combination creates that 176-day solar day. Stand on Mercury's equator, and the Sun rises slowly, taking Earth weeks to climb from horizon to zenith. It hangs there, massive and brilliant, for what feels like an eternity. Then it sets, equally slowly, and darkness falls. That darkness lasts another 88 Earth days. During those long months of night, with no atmosphere to retain even a fraction of warmth, the surface temperature drops to some of the coldest levels found on any rocky planet. The temperature doesn't just drop uniformly either. Different surface materials cool at different rates. Fresh crater ejecta, pulverized rock thrown out by impacts, cools faster than solid bedrock. Areas covered in fine dust cool differently than areas of exposed stone. This creates a complex thermal landscape invisible to the eye, but detectable by infrared instruments. Messenger's thermal mapping revealed these patterns, showing how Mercury's surface is a patchwork of different cooling rates and thermal properties. This is Mercury's first lesson in extremes. It doesn't do moderation. The planet exists in states that seem mutually exclusive. The hottest daytime temperatures in the solar system and some of the coldest nights. Both are true simultaneously in different locations. Fire on one side, ice on the other, and a terminator line between them sharper than any blade. But here's where Mercury begins to reveal its deepest contradictions. On this world of temperature extremes, on the planet closest to the Sun where daytime heat melts metal, there exists permanent water ice, billions of years old. Preserved in complete darkness, Mercury's poles hide something that fundamentally shouldn't exist: water ice, not trace amounts. Not a few molecules scattered here and there. Substantial deposits, hundreds of billions of tons, preserved for geological epochs in the last place anyone expected to find them. The discovery came from radar observations in 1991. Scientists at the Arecibo Observatory in Puerto Rico bounced radio waves off Mercury and detected highly reflective regions near both poles. The radar signature matched ice almost perfectly: high reflectivity, specific polarization characteristics, the exact properties you'd expect from frozen water. But ice on Mercury seemed absurd, like finding snow in a blast furnace, like discovering an iceberg in a volcano. The scientific community was skeptical. Some suggested the radar returns might be from sulfur deposits or unusual rock formations. Others proposed exotic minerals that could mimic ice's radar signature. But as more observations accumulated, the ice hypothesis became harder to dismiss. The reflective regions were too bright, too pure, too perfectly consistent with water ice to be anything else. Messenger, which orbited Mercury from 2011 to 2015, settled the question definitively. The spacecraft carried neutron spectrometers capable of detecting hydrogen, the key component of water. It mapped the polar regions in detail, measuring not just radar reflectivity, but actual chemical composition. The data confirmed it: water ice, thick deposits, concentrated in craters near both poles. The spacecraft also measured the locations precisely. The ice exists specifically in regions that never receive direct sunlight. These are craters with high walls and deep floors, positioned at Mercury's poles where sunlight arrives at an extremely shallow angle. The crater walls block the sun completely, casting shadows that are permanent. The key to understanding this is Mercury's axial tilt, essentially 0 degrees. Earth tilts at 23.5 degrees relative to its orbital plane, giving us seasons and ensuring that even polar regions receive some direct sunlight during summer. The Arctic and Antarctic experience midnight sun and polar night, but over the course of a year, everywhere gets some sun. Mercury stands nearly straight up and down. Its axial tilt is only about 2 arc minutes, roughly 3/100ths of a degree. This means the sun never rises high in the polar sky. At the poles, sunlight skims along the surface at a perpetually shallow angle. Any depression with walls tall enough becomes a permanent shadow zone. Some of these shadows have existed for billions of years. The crater floors have never seen sunlight, not since the craters formed from ancient impacts, not once in 4 billion years of solar system history. They are the darkest, most stable cold traps in the inner solar system, darker than the permanently shadowed craters on the moon, colder than most places in the outer solar system. Temperature in these permanent shadow regions drops to around -200 degrees Celsius. At these temperatures, water ice is as stable as solid rock. There's no mechanism for it to evaporate or sublimate. Once water molecules land in these cold traps, they freeze and remain frozen essentially forever. But the fundamental question remains: where did the water come from? Mercury formed close to the Sun in the hottest, driest region of the early solar system. The protoplanetary disk at Mercury's orbital distance would have been far too hot for water ice to exist. Any water that might have been incorporated into Mercury during formation would have been driven off by intense solar radiation. Mercury should be bone dry. The answer lies in comets. These icy bodies originate in the outer solar system, the Kuiper belt beyond Neptune, or the even more distant Oort cloud. They're essentially dirty snowballs, mixtures of water ice, frozen gases like carbon dioxide and methane, and rocky dust. Comets formed in the cold outer regions where ice is stable and abundant. Occasionally, gravitational interactions disturb these distant comets. A passing star, a near encounter with Neptune, subtle perturbations from galactic tides. These forces can nudge a comet's orbit. Some get deflected inward, falling toward the sunday. As they enter the inner solar system, solar heating vaporizes their ices, creating the characteristic glowing coma and tail. But before that happens, while they're still frozen solid, some crash into planets. When a comet hits Mercury, and this happened frequently during the late heavy bombardment about 4 billion years ago, most of its ice vaporizes instantly. The impact energy is enormous. The comet is traveling at tens of kilometers per second. The collision generates temperatures high enough to vaporize rock. Water ice doesn't stand a chance. But impacts are messy, violent events. Material scatters in all directions. Not all the water from the comet is at the impact point. Some water molecules get ejected, thrown clear of the immediate impact zone. These molecules follow ballistic trajectories across Mercury's surface. Most land in sunlight and immediately vaporize, lost to space. But a small fraction, perhaps a few percent, happens to land in those permanent shadow zones near the poles. There, protected from the sun, they freeze, and they stay frozen. This process has continued for billions of years. Every comet impact delivers more water. The delivery rate isn't constant. It was much higher during the late heavy bombardment, when the inner solar system was still being cleared of debris. But even today, occasionally, comets still hit Mercury. Each one adds a little more ice to the poles. Over geological time, the deposits accumulate. Messenger data suggests there could be 100 billion to 1 trillion tons of water ice in Mercury's polar craters. For comparison, Lake Superior, the largest of the Great Lakes, contains about 12,000 cubic kilometers of water, roughly 10 trillion tons. Mercury might have ice deposits comparable to 10% of Lake Superior's volume. The ice isn't pure water either. Radar observations show that some deposits appear brighter than others, suggesting variations in composition or structure. Some regions might be pure water ice, others might be mixtures of water with other volatile compounds, carbon dioxide, ice, frozen methane, ammonia. The darker, less reflective deposits might be ice mixed with rocky dust, or ice buried beneath a layer of regolith that partially shields it from radar. Messenger also detected hydrogen signatures consistent with organic compounds, complex carbon-based molecules, mixed with the ice. These organics wouldn't have formed on Mercury. They came from the comets. Comets carry a rich inventory of organic chemistry, including amino acids, the building blocks of proteins. When comets deliver water to Mercury, they also deliver this organic material. Some of this ice could be 4 billion years old, older than the oldest rocks found on Earth's surface, older than Earth's ocean basins, older than the continental crust. These ice deposits are time capsules from the early solar system, preserving a record of what comets were like billions of years ago. Scientists study meteorites to understand early solar system chemistry, but meteorites have been altered by their journey through space and entry through Earth's atmosphere. Mercury's ice deposits are pristine, unaltered archives. The discovery raises profound questions. If water ice can survive on Mercury in shadowed craters, where else might it exist? The Moon has similar permanently shadowed craters, and indeed, recent missions have confirmed water ice there too. Mars has ice at its poles. Even asteroids might have cold-trapped ice in shadowed regions. Water might be more widely distributed in the inner solar system than previously thought, just hidden in unexpected places. The organic compounds are equally intriguing. These molecules are chemically complex and potentially relevant to the origin of life. Nobody suggests Mercury has life or could support life. The surface conditions are far too extreme. But the fact that these compounds can survive and accumulate in protected niches tells us something important. Even in the harshest environments, chemistry can persist. Complexity can be preserved. The universe creates pockets of stability in unlikely places. This discovery fundamentally changed how scientists think about Mercury. It's not just a dead, scorched rock. It's a world with hidden complexity, with reservoirs of ancient material, with deposits that preserve a record of solar system history. The ice exists because of Mercury's extremes. The permanent shadows only exist because Mercury has no axial tilt, which is itself unusual. The extremes create the niches. The hostility creates the protection. Mercury teaches a lesson here. Contradictions can coexist. The hottest and the coldest. Fire and ice. Exposure and preservation, all on the same small world, and the contradictions go deeper. Mercury's internal structure is equally impossible, equally strange. If you could slice Mercury in half and look at a cross-section, like cutting an apple to see the core, you'd see something that shouldn't exist. The planet is essentially a giant iron ball with a thin shell of rock wrapped around it. The metal core dominates everything. The numbers are stark. Mercury's core makes up roughly 70% of the planet's mass and approximately 85% of its radius. To understand how bizarre this is, consider Earth. Our iron core represents about 32% of our mass and 30% of our radius. We have a substantial rocky mantle, about 2,900 kilometers thick. We have a solid crust, averaging 35 kilometers for continental crust, 7 kilometers for oceanic crust. These rocky layers are the dominant features of Earth's interior structure. Mercury's proportions are inverted. The core radius is about 2,000 kilometers. The rocky mantle and crust together are only about 400 kilometers thick. If Earth had Mercury's proportions, our core would reach halfway to the surface. You could drill through the mantle in a few hundred kilometers instead of a few thousand. This gives Mercury a bulk density of 5.4 grams per cubic centimeter, nearly as high as Earth's 5.5, despite Mercury being less than 40% Earth's diameter. Density equals mass divided by volume. Mercury packs an enormous amount of mass into a small space because it's mostly iron, which is much denser than rock. Granite, a common crustal rock, has a density around 2.7 grams per cubic centimeter. Iron has a density of 7.9. The predominance of iron makes Mercury unexpectedly heavy for its size. In fact, when you account for compression, the way gravity squeezes material in a planet's interior, increasing its density, Mercury's core is proportionally even more metal-rich than the raw numbers suggest. Earth's high density is partly due to gravitational compression of its much larger mass. Mercury has much lower internal pressures because it's smaller. Correcting for this, Mercury's uncompressed density would actually be higher than Earth's. This planet is metal, in a way no other rocky planet is. The standard model of planet formation cannot produce this structure naturally. When planets form from the disk of gas and dust around a young star, they accumulate materials in rough proportion to what's available. In the inner solar system, that means mostly rocky silicates with some iron mixed in. You get iron cores. Yes, iron is denser and sinks to the center during planetary differentiation. But the cores should be proportional to the overall size and composition of the available material. All the rocky planets should have similar core-to-mantle ratios if they formed from the same reservoir of material. Venus has a core that's probably about 30% of its radius. Earth is 30%. Mars is about 40% larger proportionally, which creates interesting questions, but still within the expected range. Mercury is 85%. It's not just an outlier, it's off the chart. Something removed most of Mercury's rocky material, leaving the iron core disproportionately exposed. The question that dominated planetary science for decades. What happened? The leading explanation involves catastrophic violence early in solar system history. About 4.5 billion years ago, when planets were still forming and the solar system was a chaotic mess of debris, Proto-Mercury was likely much larger. Estimates suggest it might have been 1.5 to 2 times its current mass, possibly approaching the size of Mars, which has about 11% of Earth's mass. This larger Proto-Mercury had a normal iron core and a substantial rocky mantle. It was a regular terrestrial planet, similar in composition to what would eventually become Earth or Venus. The core-to-mantle ratio was probably in the normal range, around 30%. Then something hit it. Not a small asteroid. Not even a large asteroid. Another planetary embryo. A protoplanet, perhaps 1/6 the size of Proto-Mercury, slammed into it at a velocity of tens of kilometers per second. The collision released energy equivalent to billions of nuclear weapons detonating simultaneously. Temperatures at the impact site soared to tens of thousands of degrees. Rock vaporized. The entire planet rang like a bell from the shockwaves. The impact was catastrophic enough to blast away a significant portion of Mercury's mantle. The rocky outer layers, lighter, less tightly bound by gravity, were ejected into space. Some material fell into the sunday. Some escaped Mercury's vicinity entirely, either falling into Venus or Earth during their own formation, or being lost to the solar system. The exact fate of this material is unknown, but it's gone. What remained was the dense iron core, too heavy and too tightly held by its own gravity to be completely ejected. The core survived. Some mantle material survived too, enough to create the thin shell we see today. But most of the lighter material was gone. This hypothesis, called the giant impact hypothesis, explains Mercury's high metal-to-rock ratio. It's supported by computer simulations that show such impacts are not only possible but likely during the chaotic early solar system when planet-sized bodies were still colliding frequently. The same type of giant impact likely created Earth's moon when a Mars-sized object hit proto-Earth and ejected material that coalesced into our satellite. An alternative hypothesis suggests that instead of a single catastrophic impact, Mercury lost its mantle through intense solar radiation. In the very early solar system, the young sun was more active, more violent. Powerful solar wind and intense radiation might have preferentially eroded lighter elements from Mercury's surface, while the planet was still molten or partially molten. The rocky material, being lighter and more easily ionized, could have been stripped away over millions of years, leaving the dense iron core behind. A third possibility combines both mechanisms. An impact damaged the mantle, fracturing it and making it more susceptible to erosion. And then solar wind finished the job, slowly ablating the weakened crust until only the thin shell remained. Regardless of the exact mechanism, the result is the same. Mercury is fundamentally a planetary core masquerading as a planet. It's what's left when everything non-essential gets stripped away. It's the hard kernel of a world that should have been larger, should have been different, should have had layers and protection and moderation. This has profound consequences. The large iron core gives Mercury unusual properties. It generates a magnetic field, though a weak one, only about 1.1% the strength of Earth's. This is puzzling because magnetic field generation typically requires a liquid outer core with convective motion, and Mercury is small enough that its core should have frozen solid billions of years ago. Yet, the magnetic field exists, suggesting the core is at least partially liquid and something is driving convection. Tidal heating from the sun might provide enough energy to keep the outer core molten. The magnetic field itself is oddly offset from the planet's center, shifted about 20% of the planet's radius toward the North Pole. This asymmetry is unique among the planets and poorly understood. It might result from an unusual convection pattern in the core, or from the specific geometry of the liquid-solid boundary if only part of the core is molten. The large core also affects Mercury's moment of inertia, how mass is distributed within the planet. Spacecraft tracking Mercury's gravity field reveals that mass is concentrated toward the center to an unusual degree, exactly what you'd expect from an oversized core. This concentration affects how Mercury rotates and how it responds to the sun's tidal forces. Those tidal forces are significant. The sun's gravity pulls on Mercury with enough strength to raise tides in the solid body of the planet. Not water tides like Earth's oceans experience, but deformations of the solid rock and metal. These tidal bulges dissipate energy through friction, generating a small amount of internal heat. This might be enough to keep part of the core liquid despite Mercury's small size. The massive core also makes Mercury denser than it has any right to be. Pick up a softball-sized piece of Mercury, and it would weigh as much as a softball-sized piece of Earth, despite Earth being much larger and having much higher internal pressures. Mercury is, in a very real sense, a ball of metal with a thin coating of rock, a cannonball, pretending to be a world. This structure is unique in the solar system. No other terrestrial planet comes close to Mercury's metal enrichment. It represents an end state, what you get when violent processes strip away everything but the core. Mercury is a planetary anatomy lesson, showing us what lies at the center of rocky worlds by having almost nothing else left. But Mercury isn't done revealing its strangeness. The metal ball is shrinking. The planet is actively getting smaller, and the evidence is written across its surface in massive scars. Mercury is shrinking, not metaphorically, not in geological theory, but literally getting smaller. The planet has contracted by approximately 14 kilometers in diameter over the past 4 billion years, and the process continues today. The evidence covers the surface. Massive cliff faces called lobate scarps cut across the landscape, some running for hundreds of kilometers, towering up to 3 kilometers high. These aren't the cliffs formed by impacts or volcanic calderas. They're compression features, wrinkles in the planetary crust created when the interior shrinks and the surface has to accommodate by buckling and folding. Think of a grape drying into a raisin. As the fruit loses water and volume, the skin wrinkles. The skin doesn't shrink at the same rate as the interior, so it folds and creases. Mercury's scarps are planetary scale wrinkles, the skin of a world contracting around a cooling core. The mechanism is straightforward. Mercury's large iron core generates heat through radioactive decay of elements like uranium, thorium, and potassium. This heat has been radiating into space for 4.5 billion years. As the core loses heat, it cools. As it cools, it contracts. Iron shrinks as it solidifies. The solid phase is denser than the liquid phase. Earth experiences the same process, but our larger size means we cool much more slowly. Our core is still largely molten. We're still geologically active with plate tectonics, volcanism, earthquakes. We're still, in a sense, alive as a planet. Mercury is smaller, with a larger surface area to volume ratio, meaning it radiates heat more efficiently. Small things cool faster. A cup of coffee cools faster than a bathtub of hot water. Mercury's core has been cooling for billions of years. The outer portions have already solidified. As the liquid iron freezes, it contracts. The planet's radius decreases, but the rocky crust above can't simply shrink smoothly. Rock is brittle. When forced to accommodate a smaller interior, it fractures and thrusts upward, creating these massive cliff systems. Messenger mapped over 600 major lobate scarps across Mercury's surface. They cut through craters, indicating they formed after those craters. Some scarps are relatively young in geological terms, perhaps only a few billion years old rather than the full 4.5 billion. This means the contraction has been ongoing throughout Mercury's history and might still be happening. Some scarps show fresh, sharp edges with minimal degradation from micrometeorite bombardment. This suggests recent activity, geologically speaking. Mercury might have shrunk by a few kilometers just in the last billion years. The planet is still dying, still cooling, still contracting. It hasn't reached thermal equilibrium. It won't for billions more years. The total contraction, 14 kilometers in diameter, sounds small compared to Mercury's total diameter of 4,880 kilometers. It's less than 1%, but consider what that means globally. Imagine if Earth shrank by 14 kilometers. The entire surface area would decrease. Every continent would experience compression. The crust would buckle and thrust upward. Mountain ranges would form not from tectonic plate collisions, but from global compression. Massive cliff systems would appear everywhere. That's what happened on Mercury. The whole planet experienced uniform compression. Unlike Earth's tectonics, which create localized features in specific zones where plates interact, Mercury's scarps appear globally. They form wherever the crust happened to be weak enough to fracture under the compression stress. They cut through all types of terrain, ancient cratered highlands, younger smooth plains, everything. The scarps reveal something else. Mercury never developed plate tectonics. On Earth, our lithosphere, the rigid outer shell, is broken into pieces that move independently. Plates subduct, collide, spread apart. This movement releases stress and accommodates internal changes. Mercury's lithosphere is a single, unbroken shell. When stress builds, it can't be released through plate movement. Instead, the entire shell cracks, creating these global thrust faults. This has implications for Mercury's thermal evolution. Without plate tectonics to efficiently transport heat from the interior to the surface, Mercury cools primarily through conduction, heat slowly diffusing through solid rock. This is much less efficient than the convective heat transport enabled by plate tectonics. Mercury might have stayed hotter longer than it would have with plate tectonics, but now it's cooling inexorably, locked in a one-way journey toward thermal death. The scarps also tell us about the thickness and strength of Mercury's lithosphere. The size of the cliffs, up to 3 kilometers high, indicates the lithosphere is thick enough and strong enough to support such massive features without collapsing. The spacing between scarps provides information about stress distribution in the crust. All of this helps scientists build models of Mercury's internal structure and evolution. But the contraction isn't the only thing happening on Mercury's surface. The planet has been volcanically active in the past, and the evidence suggests this activity might have continued more recently than anyone expected. Between the scarps and craters lie vast, smooth plains covering roughly 40% of Mercury's surface. These plains are volcanic in origin, ancient lava flows that flooded low-lying areas. Spectroscopic analysis from Messenger shows they're composed of basaltic rock, similar to the volcanic rocks that form Earth's ocean floors and the Moon's Maria. The volcanic activity required heat. Magma only forms when rock melts, and rock only melts when it's hot enough. For Mercury to have extensive volcanism, its interior must have been substantially hotter than it is now. The smooth plains are ancient, most formed between 4 and 3.5 billion years ago during a period of intense volcanic activity. But some regions appear younger, with fewer impact craters suggesting they formed more recently, perhaps 3 billion years ago or even later. This creates a puzzle. Mercury is small and should have cooled quickly. Conventional models suggested it lost its internal heat within the first billion years and became geologically dead. No volcanism, no tectonic activity, just a cold, inert ball slowly cooling the rest of the way. But the evidence shows volcanism continuing long past when it should have stopped. One explanation involves tidal heating. The sun's gravity creates tidal bulges in Mercury's body. As Mercury orbits in its eccentric path, sometimes closer to the sun, sometimes farther. The strength of these tides varies. The changing tides flex the planet slightly, generating friction and heat. For a small planet like Mercury, this extra heat source might have been enough to prolong volcanic activity. Another factor might be the composition of Mercury's mantle. If the mantle contains radioactive elements in higher concentrations than expected, the heat generation from radioactive decay could have sustained higher temperatures longer. Or the mantle might contain volatile compounds that lower the melting point of rock, allowing magma to form at lower temperatures than expected. Recent discoveries add another layer of strangeness. MESSENGER detected what scientists call hollows, peculiar shallow depressions with bright, fresh-looking floors that appear to be actively forming today. These hollows are small, typically a few hundred meters across and tens of meters deep. They appear clustered in certain regions, particularly in and around impact craters. The hollows are too small and too irregularly shaped to be impact craters. They don't have raised rims. They have bright, reflective floors that spectroscopic analysis suggests are composed of different material than the surrounding terrain. The leading hypothesis is that they form through sublimation, the direct transformation of solid to gas, of volatile compounds in Mercury's crust. Here's what might be happening. Mercury's crust contains sulfides and other volatile minerals. When impact craters expose these minerals to the surface, or when tectonic fracturing brings them close to the surface, the intense solar heating causes them to sublimate. The minerals vaporize and escape into space, leaving behind hollow depressions. The bright floors might be residual material left behind after the volatiles escape, or fresh rock exposed by the sublimation process. If this hypothesis is correct, the hollows represent active geological processes happening on Mercury right now. Not volcanism, not tectonics, but chemical weathering driven by solar radiation. Mercury isn't entirely geologically dead. It's transforming, slowly, under the relentless assault of the Sunday. The planet also shows evidence of explosive volcanic eruptions in its past. MESSENGER discovered pyroclastic deposits, material ejected explosively from volcanic vents scattered across the surface. On Earth, explosive volcanism happens when magma contains dissolved gases that expand violently as pressure decreases. On Mercury, the explosive eruptions might have been driven by sulfur compounds or other volatiles in the mantle. These discoveries paint a picture of a planet more complex and dynamic than the dead rock it appears to be. Mercury has been geologically active for most of its history. It experienced massive volcanic eruptions, extensive lava flooding, global compression from core cooling, and possibly ongoing surface modification through volatile loss. But the biggest surprise about Mercury's activity might be happening right now, in real time, invisible to the naked eye but spectacular when detected. The planet is evaporating. Mercury has a tail, not a metaphorical tail, not a figure of speech, but an actual luminous tail extending millions of kilometers into space, like a comet made of metal. The discovery came from ground-based observations in the 1980s. Astronomers detected a faint glow extending from Mercury's position in the sky, stretching away from the Sunday. Spectroscopic analysis revealed the glow came from sodium atoms, individual atoms of the metal sodium, glowing as they absorbed and re-emitted sunlight. The tail extends approximately 2.5 million kilometers from Mercury. That's more than 6 times the distance from Earth to the Moon. If you could somehow line up 6 moons in a row from Earth, Mercury's tail would stretch farther. It's one of the most extended atmospheric features of any rocky planet in the solar system. But calling it an atmosphere is generous. Mercury's exosphere, the cloud of atoms surrounding the planet, is extraordinarily thin. The number density at the surface is only about 10 to the power of 6 atoms per cubic centimeter. For comparison, Earth's atmosphere at sea level contains about 10 to the power of 19 molecules per cubic centimeter. Mercury's exosphere is 10 trillion times thinner. It's barely distinguishable from the vacuum of space. The exosphere contains several elements: sodium, potassium, calcium, magnesium, hydrogen, helium, oxygen. Each is present in trace amounts. The total mass of Mercury's entire exosphere is only about 10 metric tons. Less. Continue. Schadenlinglufen, than the mass of a single large truck. If you could somehow collect all the gas around Mercury, you'd have a sphere of compressed gas only a few meters across. Yet this tenuous envelope creates a tail visible from Earth with the right instruments. The key is resonant scattering. Sodium atoms absorb sunlight at very specific wavelengths, the famous sodium D lines at 589 nanometers, which give sodium vapor lamps their characteristic yellow-orange glow. Mercury's sodium atoms absorb sunlight at this wavelength and re-emit it, creating a faint but detectable glow against the blackness of space. Where does this sodium come from? It's not leaking from Mercury's interior. The answer lies in the violent interaction between Mercury's surface and the space environment. Mercury sits deep in the Sun's gravity well, meaning it's exposed to intense solar radiation and solar wind. Solar wind is a stream of charged particles, protons, and electrons, flowing outward from the Sun at speeds of 300 to 800 kilometers per second. When these high-energy particles slam into Mercury's surface, they transfer momentum to atoms in the rocks. Most of the time, the energy isn't sufficient to dislodge surface atoms. But occasionally, a solar wind particle hits with exactly the right energy and angle to knock a surface atom free. The atom escapes from the rock and enters Mercury's exosphere. This process is called sputtering. Solar wind isn't the only mechanism. Sunlight itself can dislodge atoms through a process called photon-stimulated desorption. High-energy ultraviolet photons from the Sun hit the surface and transfer enough energy to break chemical bonds, freeing individual atoms. Mercury receives about 7 times more solar radiation than Earth, meaning this process is much more effective than it would be at our distance from the Sunday. Micrometeorite impacts also contribute. Tiny particles of dust and debris constantly rain down on Mercury's surface. Each impact vaporizes a small amount of rock, ejecting atoms into the exosphere. Mercury lacks an atmosphere to burn up these meteoroids, so they hit the surface directly at full cosmic velocities, up to 70 kilometers per second. Each impact is like a microscopic explosion, throwing atoms into ballistic trajectories above the surface. Once freed, the atoms follow complex paths. Mercury's weak gravity can't hold them permanently. Many escape entirely, but before they do, they travel in arcing trajectories, sometimes rising hundreds of kilometers above the surface before falling back down. Some atoms collide with the surface and stick. Others bounce and are re-ejected. Others gain enough energy to escape Mercury's gravity altogether. The sodium atoms that escape drift away from Mercury, but they don't travel randomly. The Sun's radiation pressure, the physical push from sunlight, acts on them. Photons carry momentum, and when they're absorbed by an atom, that momentum transfers. For light atoms like sodium, radiation pressure can be significant. The pressure always points radially away from the Sunday. Sodium atoms, leaving Mercury, are therefore pushed outward, away from the Sun, creating the tail. The atoms stream behind Mercury as it orbits, forming an elongated cloud that points perpetually away from the solar direction, just like a comet's tail. The tail isn't static. It changes with Mercury's orbital position and solar activity. When Mercury passes through regions of enhanced solar wind, coronal mass ejections, or solar storms, the sputtering rate increases and the tail brightens. When Mercury is at perihelion, its closest approach to the Sun, the radiation pressure is stronger and the tail extends farther. The tail is a dynamic feature, responding in real time to space weather. But the sodium tail is only the most visible part of a larger phenomenon. Mercury is losing material constantly through multiple processes. Helium in the exosphere comes from the solar wind, alpha particles that hit the surface and are neutralized, becoming helium atoms. These escape quickly because helium is so light. Hydrogen also comes from solar wind protons. Calcium, magnesium, and other heavier elements come from sputtering of Mercury's crust. Messenger measured the exosphere composition in detail. The spacecraft discovered that the exosphere's composition varies with location. The day side is enriched in sodium and potassium, lighter elements more easily freed by sunlight. The night side shows more calcium and magnesium, suggesting temperature-dependent processes are at work. Near the poles, The exosphere is thinner overall, perhaps because lower solar radiation means less sputtering. The exosphere also shows latitude variations related to Mercury's magnetic field. The weak planetary field creates a small magnetosphere, a region where charged solar wind particles are deflected. This magnetosphere is tiny compared to Earth's, only about 1 Earth radius on the day side before the solar wind compresses it, but it provides some shielding. Regions where field lines are open, connected to the solar wind, rather than closed loops, experience more intense particle bombardment. These regions show enhanced exosphere production. Regions protected by closed field lines experience less bombardment and produce less exosphere. Messenger's measurements revealed these patterns, showing how the magnetic field shapes the exosphere distribution. The calcium in the exosphere creates its own tail, though much fainter than sodium's. Calcium atoms are heavier and less easily pushed by radiation pressure, so the calcium tail is shorter. Magnesium shows similar behavior. The result is that Mercury is surrounded by multiple overlapping tails of different elements, each with its own characteristics. The total mass loss rate from Mercury is estimated at several hundred kilograms per second, perhaps 300 to 500 kilograms every second continuously. Over the course of a year, that's about 10 to 15 million kilograms. Over Mercury's 4.5 billion year history, the total mass lost might be on the order of tens of trillions of kilograms. That sounds like a lot, but Mercury's total mass is 3.3 times 10 to the power of 23 kilograms. The mass lost is utterly negligible compared to the total, less than 1 part in 10 billion. Mercury isn't going to evaporate completely or even shrink measurably from this process. But the fact that it's happening at all is remarkable. The planet is being slowly sandblasted by the solar wind and solar radiation. Every second, hundreds of kilograms of Mercury's surface atoms are ejected into space. Some fall back, many escape forever. The surface is constantly being refreshed as atoms are removed and new material is exposed. This means the very top atomic layers of Mercury's surface are very young, even though the rocks themselves are billions of years old. This process creates one of the most dynamic environments in the solar system. The exosphere responds to solar storms within minutes. The tail brightens and dims with solar activity. The composition shifts with temperature and solar wind conditions. Mercury's tenuous atmosphere is constantly being created, destroyed, and recreated in an ongoing cycle driven by the sun's energy. The sodium tail is visible from Earth using specialized instruments, narrowband filters tuned to the sodium D lines. Amateur astronomers with the right equipment can sometimes detect it. From space, it's spectacular. Messenger observed the tail from various angles, watching it stream behind Mercury like a luminous banner. The tail also revealed something unexpected: structure. Instead of a smooth gradient of sodium atoms, the tail shows clumps and streams, regions of higher and lower density. These might result from bursts of enhanced sputtering during solar storms, or from the rotation of Mercury creating source regions that come and go, or from complex dynamics in the exosphere itself. The entire phenomenon is essentially Mercury's slow evaporation. The planet is bleeding atoms into space, not enough to matter gravitationally, but enough to create this beautiful, ghostly tail. Mercury is a metal comet, a planet becoming a cloud, a solid world slowly dissolving into the void. And this brings us to perhaps the strangest contradiction of all. How do we get there? How do we send spacecraft to witness these phenomena up close? Because despite being our closest planetary neighbor, Mercury is the hardest place to reach in the solar system. Bepi Colombo launched on October 20th, 2018. It won't arrive at Mercury until December 2025. 7 years to travel to our closest planetary neighbor, a planet only 58 million kilometers away at closest approach. For comparison, NASA's Perseverance rover reached Mars in about 7 months. Voyager 2 reached Neptune in 12 years. Neptune is 30 times farther from the Sun than Earth. New Horizons reached Pluto in 9.5 years. Pluto orbits 40 times farther out than Earth does. Why does Mercury take so long? The answer lies in orbital mechanics and the Sun's gravity well. Reaching another planet isn't like driving to a destination on Earth where you point in the right direction and go. It's a problem of orbital energy and velocity. Earth orbits the Sun at about 30 kilometers per second. To reach Mars, which orbits slower at about 24 kilometers per second, a spacecraft needs to speed up slightly to enter a higher, slower orbit that intercepts Mars. This is relatively straightforward. To reach Mercury, which orbits at 48 kilometers per second, the naive approach would be to speed up even more. But here's the problem. Speeding up raises your orbit, taking you farther from the Sunday. To get closer to the Sun, to reach Mercury's orbit, you actually need to slow down. Slowing down from Earth's orbital velocity to Mercury's orbital velocity requires an enormous change in speed, about 26 kilometers per second of delta V, the measure of how much velocity change a mission needs. For comparison, landing humans on the Moon required about 17 kilometers per second of delta V. Getting to Mercury requires 50% more. No rocket can directly provide that much delta V. The fuel required would be prohibitively massive, hundreds or thousands of tons. The spacecraft would be mostly fuel tank with barely any room for instruments. It's technically possible, but economically and practically infeasible. So missions to Mercury use gravity, assists flybys of other planets that change the spacecraft's velocity without burning fuel. The spacecraft flies close to Venus or Earth, using the planet's gravity to alter its speed and direction. Each flyby changes the orbit slightly, gradually reducing the orbital energy until the spacecraft can match Mercury's orbit. But gravity assists take time. Each one requires waiting for the right planetary alignment, then flying to the assisting planet, then waiting for the next alignment. Bepi Colombo's trajectory includes 1 flyby of Earth, 2 of Venus, and 6 of Mercury itself, before finally settling into orbit. That's 9 separate gravitational encounters over 7 years. The trajectory looks insane when plotted. The spacecraft doesn't fly in a straight line or even a simple curve. It loops around the inner solar system in a complex path that intersects Earth's orbit, then Venus's orbit twice, then Mercury's orbit 6 times, with each loop going deeper into the Sun's gravity well. After the Earth flyby in April 2020, Bepi Colombo flew to Venus for flybys in October 2020 and August 2021. Each Venus encounter slowed the spacecraft slightly, lowering its orbit's minimum distance from the Sunday. Then came 6 Mercury flybys starting in October 2021, each one slowing the spacecraft more until finally, in December 2025, it will have bled off enough energy to enter orbit. The total distance traveled, 8.5 billion kilometers. To reach a planet only 58 million kilometers away, the spacecraft will travel 146 times farther than the direct distance. It's like walking from New York to Los Angeles by way of Moscow, Beijing, Sydney, Cape Town, and back multiple times. Why is this necessary? Why can't the spacecraft just fly straight there and use its rockets to slow down? The answer is the Sun's gravity well. Think of the solar system as a funnel. Earth sits partway down the slope. Mercury sits much deeper. To get from Earth to Mercury, you have to descend deeper into that funnel. Descending requires losing orbital energy, slowing down relative to the Sunday. But here's the trick. Slowing down relative to the Sun means you're actually falling toward it. If you slow down too much, you'll just fall into the Sunday. You need to slow down exactly enough to match Mercury's orbital velocity at Mercury's distance. Too much, and you crash into the Sunday. Getting this precisely right requires careful choreography. Each gravity assist provides a tiny nudge in the right direction. The spacecraft gradually spirals inward, losing energy bit by bit, until finally it's moving slow enough at Mercury's distance to be captured by Mercury's weak gravity. The energy requirements explain why it's actually easier to leave the solar system than to reach Mercury. New Horizons launched with enough velocity to escape Earth's orbit and eventually leave the solar system entirely. It reached Pluto in under a decade. Escaping is relatively easy, you just need to go fast enough. But falling toward the sun in a controlled way is hard. You're fighting against the sun's gravity, trying to pull you in too fast. You need to constantly adjust your trajectory to maintain the delicate balance between falling sunward and maintaining orbital motion. Bepi Colombo carries its own propulsion system, solar electric thrusters that use solar panels to generate electricity that ionizes xenon gas and expels it at high speed. These thrusters produce only a tiny amount of force, about 290 millinewtons, roughly the weight of an AA battery pressing on your hand, but they can run continuously for years. The spacecraft uses these thrusters between gravity assists to fine-tune its trajectory. It fires them for months at a time, slowly altering its orbit with their gentle but persistent push. The combination of gravity assists for major velocity changes and ion thrusters for fine adjustments enables the mission to reach Mercury with a practical amount of fuel. Even surviving near Mercury requires specialized technology. The spacecraft carries a massive heat shield to protect against the intense solar radiation. Near Mercury, solar intensity is about 11 times stronger than at Earth. Electronics would overheat and fail without protection. Solar panels would generate too much power and damage themselves. Bepi Colombo's heat shield is made of advanced ceramics and insulation. It keeps the spacecraft's main body in shadow, allowing radiators to shed excess heat into space while the shield faces the sunday. The design is elegant, but necessary. Without it, the spacecraft would cook. Messenger, the previous mission, used a similar strategy. It carried a sunshade made of ceramic fabric that could withstand temperatures up to 400 degrees Celsius. The spacecraft oriented itself to keep the shade between its instruments and the sun at all times. Its solar panels were designed to be less efficient at high intensities, preventing overload. Both missions also had to deal with Mercury's proximity to the sun during communications. The sun's corona, its outer atmosphere, extends millions of kilometers. When Mercury passes behind the sun from Earth's perspective, a geometry called superior conjunction, the spacecraft is trying to send signals through the corona. The charged particles in the corona scatter and absorb radio waves, creating noise that can overwhelm the signal. During these periods, communication becomes difficult or impossible. Missions to Mercury spend weeks at a time out of contact, operating autonomously, trusting their programming to keep them safe until Earth comes back into view. The orbital mechanics near Mercury are also complicated by the sun's gravity. Mercury orbits so close to the sun that general relativity becomes important. Einstein's equations predict that Mercury's orbit precesses. The ellipse slowly rotates by 43 arc-seconds per century more than Newtonian physics predicts. This tiny effect was one of the first confirmations of general relativity. For a spacecraft orbiting Mercury, these relativistic effects must be included in trajectory calculations. Newtonian mechanics alone aren't accurate enough. The spacecraft's orbit planning software includes relativistic corrections to ensure accurate predictions. Mercury's weak gravity presents another challenge. The planet's escape velocity is only 4.2 kilometers per second, less than half Earth's escape velocity. This means a spacecraft in low Mercury orbit needs much less velocity than in Earth orbit, but it also means Mercury's gravity has a weak hold. Perturbations from the sun's gravity can easily disrupt orbits. Messenger dealt with this by using a highly elliptical orbit, 200 kilometers at closest approach, up to 15,000 kilometers at furthest. This orbit was deliberately designed to be unstable in a useful way. The sun's gravity would perturb it, but those perturbations were predictable and could be countered with occasional thruster firings. Bepi Colombo will deploy 2 separate spacecraft into different Mercury orbits. The Mercury Planetary Orbiter will study the surface and interior from a polar orbit. The Mercury Magnetospheric Orbiter will study the magnetic field and exosphere from a highly elliptical orbit. Coordinating 2 spacecraft at Mercury adds another layer of complexity. The engineering required for Mercury missions is extraordinary. Every component must survive temperature extremes. Solar panels must work at 11 times normal solar intensity. Communications must function when the sun's corona interferes. Navigation must account for relativistic effects. The spacecraft must operate autonomously for weeks when Earth is out of contact. And all of this, the 7-year journey, the 9 gravity assists, the 8.5 billion kilometers traveled, is just to deliver a few hundred kilograms of instruments to Mercury orbit. Why go to all this trouble? Why invest hundreds of millions of dollars and 7 years of flight time to reach this small, extreme, apparently dead world? Because Mercury teaches us things we can't learn anywhere else. Mercury doesn't make sense. It shouldn't have ice on the hottest planet. It shouldn't be mostly metal with barely any rock. It shouldn't be shrinking while also evaporating. It shouldn't be harder to reach than the edge of the solar system, despite being our closest planetary neighbor. Every property of Mercury contradicts some intuition we have about how planets work. And that's exactly why it matters. Science progresses at the boundaries, the things we understand well, Earth-like conditions, moderate temperatures, familiar compositions. Those teach us about the common cases. Mercury teaches us about the extremes. It shows us what's possible when conditions are pushed to their limits. Consider the ice. For decades, scientists assumed water ice couldn't exist in the inner solar system except on Earth. Too hot, too much solar radiation. The paradigm was simple. Ice belongs in cold places, and the inner solar system isn't cold. Mercury shattered that assumption. Ice can exist anywhere there's a cold trap, a location where temperature stays low enough for long enough. On Mercury, those cold traps are craters that never see sunlight. On the Moon, similar cold traps exist. Asteroid surfaces might have them in permanently shadowed regions. This realization changed how we think about water distribution. Water might be more common than we thought, just hidden in unexpected places. That has implications for future space exploration. If ice exists on Mercury, it might exist on other airless bodies closer to Earth, providing resources for future missions. It also changed how we think about organic compound preservation. The organic molecules detected in Mercury's ice shouldn't have survived this close to the Sunday, but protected in those craters, they persisted for billions of years. If complex chemistry can survive on Mercury, it can survive in other extreme environments. This matters for astrobiology, the search for life beyond Earth. We've been looking in the obvious places: Mars, because it has a familiar climate; Europa and Enceladus, because they have liquid water oceans. But Mercury hints that we should also look in contradictions, in places where extreme hostility creates pockets of protection. Life requires liquid water, organic compounds, and energy. Mercury has no liquid water and never could. It's too extreme. But it shows that 2 of those 3 ingredients can exist in surprising places. Maybe we should look for life in locations we dismissed as too hostile, if those locations have protective niches like Mercury's shadows. The metal core teaches different lessons. Planetary formation models assume certain ratios of rock to metal based on solar nebula composition. Mercury violates those ratios. This tells us planet formation isn't a gentle, orderly process where materials accumulate in predictable proportions. It's violent, chaotic. Planets collide with each other. Massive impacts strip away entire mantles. The early solar system was a demolition derby where protoplanets smashed together and the survivors were often damaged, stripped-down versions of what they should have been. This violence explains things about Earth. Our moon probably formed from a giant impact. Earth's iron core is slightly larger than models predict. Perhaps we also lost some mantle material during formation, just not as much as Mercury. Mars's large core might indicate it suffered impacts too. Mercury is an extreme example, but it reveals that violent collisions were common. Every terrestrial planet probably experienced major impacts during formation. We're all survivors of cosmic catastrophe. We're just less obviously damaged than Mercury. The shrinking teaches us about planetary cooling and lifespan. Earth will eventually cool completely too. Our core will freeze, magnetic field will disappear, plate tectonics will cease, volcanic activity will end, we'll become geologically dead, like Mercury. It won't happen for billions of years, Earth is large enough to stay active for a long time. But Mercury shows us the end state, the final condition of a rocky planet. Frozen core, wrinkled crust, no activity except slow cooling. It's a preview of Earth's distant future. The evaporation, the sodium tail, and exosphere demonstrates that planets interact with their environment constantly. We think of planets as isolated objects, but they're not. Solar wind constantly sandblasts the surfaces of airless bodies. Radiation pressure pushes atoms into space. Magnetic fields deflect charged particles or channel them toward poles. Mercury's exosphere is created and destroyed continuously. The atoms we see today aren't the same atoms that were there yesterday. The surface is constantly being refreshed. This happens on the Moon too, on asteroids, on all airless bodies. Mercury just makes it visible because it's so close to the Sun that the process is intense enough to create a visible tail. Understanding this helps us interpret observations of other bodies. When we detect sodium or potassium in the exosphere of the Moon or asteroids, we know it's being actively sputtered from the surface. We can calculate loss rates and surface composition from exosphere measurements. And the journey, the 7-year flight, the complex trajectory that teaches humility. We've been to the Moon, we've landed rovers on Mars. We've sent probes past Jupiter and Saturn and Uranus and Neptune and Pluto. We've sent Voyager into interstellar space. But our nearest neighbor, the planet visible from Earth with naked eyes at dusk, that took 2 spacecraft across 50 years to visit just a handful of times. We can barely get there. Reaching Mercury is harder than reaching the edge of the solar system. This reminds us that space is vast and difficult and doesn't care about our intuitions. Proximity doesn't mean accessibility. The obvious isn't always the easiest. The Sun's gravity well creates barriers that are harder to overcome than simple distance. It also reminds us that when we do overcome those barriers, we learn things worth knowing. Messenger discovered the ice, mapped the scarps, measured the exosphere, revealed the magnetic field's strange asymmetry. Bepi Colombo will discover more. Every mission to Mercury has revolutionized our understanding because we knew so little before. Mercury teaches us to question assumptions. Ice can exist on the hottest planet. Metal planets are possible. Closer isn't easier. Extremes create complexity. Dead planets still tell living stories. These aren't just facts about Mercury. They're lessons about how to think about the universe. When something seems impossible, look closer. It might just be unlikely. When something breaks the rules, ask which rules and why. When conditions seem too extreme for anything interesting, look for the niches and exceptions. The universe is full of contradictions. Mercury just makes them obvious. But there's one more thing Mercury teaches us, and it's the most important: that we looked. That we sent spacecraft across 7 years and 8 billion kilometers to understand one small world. That we invested engineering expertise and money and time to answer questions about a planet that will never be colonized, that has no economic value, that offers us nothing except knowledge. We did it anyway. We went to Mercury because it was strange and we wanted to know why. That curiosity, that drive to understand even when there's no practical benefit, that's the human signature written across the solar system. Step outside again on a clear evening. Look for Mercury on the western horizon just after sunset. That small, bright point is still there, still twinkling in the dusk. But now you know what it is. You know about the 600-degree temperature swing, the binary world that's either furnace or freezer with nothing between. You know about the ancient ice, hiding in eternal shadows, preserved for billions of years in the most unlikely place. You know about the giant metal core, the exposed heart of a world stripped down to essentials by cosmic violence. You know the planet is shrinking, wrinkling like aging skin as its interior cools. You know it's evaporating, bleeding sodium atoms into space and creating a glowing tail millions of kilometers long. You know it's one of the hardest places in the solar system to reach despite being our closest neighbor. Mercury doesn't look different. It's still just a point of light in the twilight sky, but your understanding has changed. That dot isn't just a hot rock anymore. It's a world, complex, strange, full of contradictions that challenge everything we thought we knew about planets. And somewhere out there, between here and Mercury, Bepi Colombo is traveling. Right now, as you read these words, it's somewhere in the inner solar system, executing its carefully choreographed journey. Its ion thrusters might be firing, producing that tiny gentle push that will gradually, over months and years, lower its orbit enough to reach Mercury. The spacecraft is autonomous. No one is flying it in real time. Signals take too long to make manual control practical. It's following programming, making decisions based on sensor readings, adjusting its trajectory without human input. A machine intelligence guiding itself through the void toward a destination years away. When it arrives in late 2025, it will deploy 2 separate spacecraft into Mercury orbit. They'll study the surface, the interior, the magnetic field, the exosphere. They'll answer questions we've been asking for decades. They'll discover things we haven't thought to ask yet. Scientists will spend years analyzing the data. They'll write papers, build models, argue about interpretations. New PhD students will base their dissertations on Bepi Colombo discoveries. The knowledge will accumulate slowly, one measurement at a time, one insight at a time. But the knowledge itself isn't the point. Or rather, it's not the only point. The point is that we looked at Mercury, this extreme, hostile, difficult world, and decided we wanted to understand it. That we invested creativity and engineering and resources into a mission that has no economic return, no strategic value, no practical benefit except knowing. That's the human thing. That stubbornness about mystery. That refusal to accept I don't know as a final answer. We could have looked at Mercury, shrugged, and moved on. Focused on Mars where we might someday live, or Europa where we might find life, or asteroids where we might mine resources. But we didn't. We went to Mercury too, because it was there and we didn't understand it, and that was enough reason. Earth is a gentle planet. We have thick atmosphere that moderates temperature and protects us from radiation. We have liquid water oceans that regulate climate. We have a strong magnetic field that deflects solar wind. We have plate tectonics that recycle carbon and maintain a stable environment over geological time. We're protected, cushioned. We exist in a narrow band of conditions where life is not just possible but easy. Water stays liquid. Temperatures stay moderate. Seasons change gradually. Weather is usually survivable. Mercury has none of these comforts. It's a naked planet, exposed directly to space, experiencing extremes that would be instantly lethal to any life we know. It's everything Earth isn't: hostile, variable, unprotected, and yet, there's ice in the shadows. There's complex chemistry preserved in cold traps. There's geological activity in the form of shrinking and potentially ongoing hollow formation. There's a magnetic field generated somehow in that massive core. There's a dynamic exosphere responding to solar conditions. Mercury isn't dead. It's just extreme. It's still changing, still interacting with its environment, still telling a story if you know how to listen. The story it tells is about limits, about how far conditions can be pushed before nothing can survive, about what happens at the boundaries of the possible. Mercury lives at those boundaries. The hottest days, the coldest nights, the thinnest atmosphere, the largest core, the deepest in the sun's gravity well. It exists at the edge of what a terrestrial planet can be and still be a planet. Any closer to the sun and it might have evaporated completely. Any more violent an impact and it might have been destroyed entirely. It's balanced on a knife edge of existence. And from our gentle world, with our protective atmosphere and moderate climate, we look at Mercury and we learn. We learn what the limits are. We learn how nature handles extremes. We learn that contradictions can coexist, that assumptions can be wrong, that the universe is stranger and more varied than our earthbound experience suggests. We learn humility too. We've been to Mercury exactly twice in all of human history. Brief flybys in the 1970s and one orbiter mission. Our current mission won't arrive for years. Our closest neighbor remains largely unexplored, still mysterious despite decades of study. Space is hard. The solar system is vast. Reaching our own moon was an extraordinary achievement. Reaching Mars with rovers is impressive. Reaching Mercury is nearly as difficult as reaching the outer planets, but we keep trying. Messenger finished its mission in 2015 when it finally ran out of fuel and crashed into Mercury's surface. The first human-made object to impact Mercury. It's still there. A small crater in the regolith, metal and silicon slowly being buried by micrometeorite impacts. Bepi Colombo will join it eventually. When its fuel runs out and its mission ends, it will either crash into Mercury or be left in an unstable orbit that eventually decays. Another piece of human technology will become part of Mercury, adding our atoms to that evaporating tail, mixing our silicon and aluminum with Mercury's ancient iron. It's a kind of immortality. Long after Bepi Colombo ceases functioning, long after the scientists who built it have died, long after the data is forgotten, some atoms from Earth will still be there on Mercury, slowly being sandblasted by solar wind, slowly evaporating into the sodium tail, slowly drifting away into space. In a few billion years, when Mercury's core has completely frozen and its surface has stopped shrinking, when the scarps have been buried under billions of years of micrometeorite impacts, when the solar system has changed in ways we can't predict, those atoms will still be there. Or rather, the dance of those atoms, recycled through geological processes, will be incorporated into Mercury's crust. That's what exploration does. It physically connects us to the places we visit. We leave traces. We become part of the worlds we study. But the real connection isn't physical. It's knowledge. It's understanding. It's the way Mercury has changed from a mysterious point of light to a world we comprehend, at least partially. We've mapped its surface, measured its composition, studied its magnetic field, watched its exosphere shimmer and flow. We've understood it well enough to send spacecraft there, to predict where they'll be years in advance, to command them across billions of kilometers with signals that take minutes to arrive. That's the real achievement. Not the hardware, impressive as it is, not the data, valuable as it is, but the understanding, the way we've taken this extreme, alien world and made it familiar enough to visit, the way we've learned its rules and worked within them. Mercury is still strange. It still breaks our intuitions about how planets work. It's still full of mysteries waiting to be solved, but it's no longer completely alien. It's a place we've been, a place we've studied, a place we understand well enough to ask better questions. And in a few years, when Bepi Colombo arrives and begins its primary mission, we'll understand it even better. We'll discover new contradictions, new extremes, new lessons about what's possible in the universe. The story of Mercury isn't finished. It's barely begun. We've had 2 missions across 50 years. We might have 10 missions across the next century. Each one will reveal more, teach more, surprise more. But the core story, the story of humans looking at the extremes and wanting to understand them, the story of traveling impossible distances just to learn, the story of our curiosity about places we'll never live and conditions we'll never experience, that story is already written. It's written in the trajectory of every spacecraft, in every measurement, in every image sent back across millions of kilometers. It's written in the fact that Bepi Colombo exists at all, that someone designed and built and launched a machine to spend 7 years traveling to a place humans will probably never visit in person. Mercury doesn't care that we study it. It will continue its slow death regardless of whether we watch. The core will keep cooling. The surface will keep shrinking. The exosphere will keep evaporating. The ice will keep waiting in its shadows. But we care, we watch, we study, we learn, and that caring, that curiosity about places beyond our survival needs, that drive to understand even when understanding offers no reward except itself, that's what makes us human. Mercury is still there in the evening sky, still twinkling, still waiting, and we're still watching, still wondering, still preparing the next mission, the next discovery, the next question. The smallest planet, the biggest mysteries, our closest neighbor, our hardest destination, Mercury, the extreme planet that taught us to look for contradictions, to question assumptions, to explore not despite difficulty but because of it, the ancient ice preserved in fire, the metal heart exposed by violence, the shrinking world that's simultaneously evaporating, the impossible journey to the nearest place, all of it real, all of it waiting, all of it teaching us what's possible when nature is pushed to its limits, and teaching us, too, what's possible when human curiosity is given the chance to reach across the void.